So, so we were talking about the techniques to go from base 10 to binary. And I gave you previously the example of 9. Okay, and we said that we will try to combine. Also, you can say that 9 was 8 plus 1. Instead of writing 8, if you write 8 as 2 times 4, it will not work. But if you pay attention that 8 is 2 to the power 3 and 1 is 2 to the power 0, then you can directly say, deduce that 9 can be written as 1, 0, 0, 1. If you didn't pay attention for this combination, let us try to do it together. You just say 9 over 2. It will give me 4. And the remainder is 1. Now I will take 4. So I will do 4 over 2. 4 over 2 will give me 2, and the remainder is 0. Now I take 2. 2 over 2 will give me 1, and the remainder is 0. And finally, I take 1. So 1 over 2 will give me 0, and the remainder is 1. And I stop here because I reached 0 here. So I can stop. And then I read from bottom to top, I get 1, 0, 0, 1. So I will get, of course, the same result. Okay? So in case the number is very complex, it's more convenient to use this method. In case the number is simple, I can just try to find combination of how can I write the number with 2 power something with numbers 0 and 1, then it's fine. I can do it in this way. Okay. Now, let us move to the case where we have a decimal number and we want to convert from decimal to binary. Okay, so in case I have a decimal number as 0.1, I will do the opposite procedure. Instead of dividing by 2, I will multiply by 2. So I will start to do 0.1 times 2. I get 0.2. In case I get a number smaller than 1, I will take it as it is. In case I get a number higher than 1, I subtract 1 and I take the remainder. Okay? So now 0.1 times 2 gives me 0.2. I will take 0.2. I multiply again by 2. I get 0.4. 0.4 is smaller than 1. I take it as it is. I multiply by 2. I get 0.8. 0.8 is smaller than 1. I can take it as it is. I multiply by 2. I get 1.6. I will stop here. 1.6 is larger than 1. I subtract 1. It will give me 0.6. I take 0.6 here. I multiply by 2, it will give me 1.2, which is higher than 1. So I subtract 1, I get 0.2. I multiply by 2, I get 0.4. It doesn't seem to stop somewhere. In order to stop, if I want to stop, the condition is that I reach exactly 1 somewhere here. If I don't reach exactly 1, I cannot stop. Okay? But here, if you look at the sequence, you can see that I have 0.2 only is not repeating, but after 0.2 I have 0.4, 0.8, 1.6, 1.2. Again, 0.4, 0.8, 1.6. If I continue, I will get 1.2, and then the series will be repeated, 0.4, 0.8, 1.6, 1.2. It will be a never-ending series, okay? So now, if you want to write what is 0.1 in base 2, then all you have to do after doing this, you put 0, decimal point, and then you read from top to bottom, in opposite with the previous case, when you have integers. So you read from top to bottom, you have 0, 0, 0, 1, 1, 0, 0, 1. You can continue, because look, just as I told you, the first, you can consider that just the first part is not repetitive. Okay, but once I have 0.4 here, it's repeating 0.4, 0.8, 1.6, 1.2, 0.4, 0.8, 1.6, 1.2. So I have first, just the first one is not in the sequence. Then I have 0, 0, 1, 1, 0, 0, 1, 1. So that's it. 0, 0, 1, 1, 0, 0, 1, 1. It's infinite. You can repeat it in an infinite way. So this is, as you can see, this will induce round-off errors. Because as we took the example of the digital clock last time, we said it's true that 0.1 is it's a finite number in decimal base, while in binary base we have infinite digits after the decimal point. So this is why your calculator at the end will work with binary, and then when it got the result, it will transform it back to decimal system for displaying the result. So when it will do this operation of going first from decimal base to binary base, then go back to decimal base, you will have a certain round of error, okay, as we have seen last time, okay? So the round of error will be induced by this, plus of course that we have the calculator can just store a certain number of digits. So now let us take another example where we have a finite number after the decimal point. If I want to write 0.125 in binary base, so I will do the same technique. I first multiply by 2. I get 0.25. Smaller than 1, I take it as it is. I multiply by 2. I get 0.5. Smaller than 1, I take 0.5 as it is. I multiply by 2. I get 1. 1 exactly. If I get 1 exactly, I stop here. Why I stop when I get 1 exactly? Because if I have just a number smaller or equal to 1, I subtract 1. And here, if I subtract 1, I get 0. So now, 0 times 2 is 0, and I will have then infinite zeros. But you know that these zeros will be to the right of 1, which is after the decimal point. So I don't, these zeros will not affect my result. So I can stop here, and then to read the number, I just put 0 decimal point, and I read 0, 0, 1. Okay. So any question on how to convert from base 10 to base 2? Okay. Let us now take some examples. If I want to add numbers, let's say, if I have to compute what is 7.1 in base 10, what is 7.1 in base 2, what the general rule is just to divide it into integer and decimal number. So I separate the two parts. I know that 7 in base 10, I can calculate it, or with experience, I will know what it is. So here it's 111. And for 0.1, I have just computed what is 0.1. So just when you add them, the part before the decimal point will be the integer part, and the part after the decimal point is this one. Okay. Now, for example, I can ask you, let's say I ask you to add 1.111 in base 2 plus 101 in base 2. You have certain rules, new rules for these additions. So to know, if you don't know these rules, it's what you can do. You can say, I will convert this number. Okay, so in base 10, I know that 111 is 7. And this number 101, it's 2 power 0, 1. So it's 1 plus 2 power 2, which is 4. It's 5. So this is 5. So I can say the summation of these two is 7 plus 5. In decimal, you work easily. 7 plus 5, you can directly say it's 12. And then you convert back 12 to base 2. So no need to learn if you want all the properties of base 2, how to do the addition, because it's something new for you. You cannot do it in your mind directly. So the better thing you can do, you can go back to the decimal base, do the addition, and then convert back to base 2. Okay. Of course, we can develop rules to do additions in base 2, but our mind can do easily additions in decimal base. Now, let us, after defining this, we will move to see how we can have round of errors when we add numbers. Okay, so this will depend on the storing numbers on the computer. So the largest number that can be read by a computer is around 9 times 10 to the power 307, which is really a large number. Now, if we exceed this number, we can get the following symbol. The following symbol, non-defined. Okay. So when we get these symbols, it's not a number. This means that it's an infinite number. And my computer cannot read it anymore. So in this case, you will have this symbol when you have a divergent solution, or when you have a number that will exceed the capacity of your computer. So similarly, smallest number that can be read is around 2.23 times 10 to the power minus 308. And anything smaller than this number will be 0. Of course, these computers that we are talking about are powerful computers, not old computers. And in case of calculator, or in case of we use a certain software as MATLAB, the accuracy will be much smaller. Okay, we will see together now. Now, this is a very large range, but sometimes we can see that even if we have very high precision machine, when we add very high number to very small number, we still can have some errors. And let us see examples about it. So now, if I want to determine what is the machine precision, okay, what is the machine precision that I have, okay? So here, what we are presenting here is the number of digits that the computer can read, okay? So let's say my computer can just read one digit, okay? So if I compute in base, so let's say I know that in base 2, okay, I just have 2 to the power n, okay? Here I'm talking about points after the decimal point. So let's say I am reading the number as 0 point something, okay? So if I am working with just one number, of course my accuracy will be of the order of 1/2 of 0.5, and I cannot read then numbers smaller than 0.5. Now, the larger the number of digits I can read, okay, the higher will be my precision. And to know what will be the smallest number I can read, okay, I can, let's say, perform this small exercise. So I will say that, let's say if I can read after the dot 2 numbers, then x will be equal to 1/2 to the power 2, which is 0.25. And I will repeat this for any n after the decimal point. Okay, now if I do y equals to 1 plus x, I expect to get a number higher than 1. Analytically, of course, always I will have 1 plus x larger than 1 because x is different than 0. But in my computer, it depends on the number of digits my computer can store. If I exceed the number of digits that my computer can store, I will not read the number higher than 1. I read it just equal to 1. Here, for example, if my computer can store 51 digits, then of course I will have to continue here, and then I will have a certain number. But to be able to see it here directly, we computed y minus 1. Analytically, y minus 1 should give me x, exactly x. But my computer, if the number of digits will exceed the capacity of my computer will not read it, it will just read 0. So if I want to know what is the machine precision, I can just do the small calculations. So I do 1/2 to the power n. So I write x as one. If I'm working in binary system, okay, I have x equal 1/2 to the power n, and I will try what is the number that my computer will read. Okay, so I will look at y minus 1. If I'm just reading the value of x, then my computer is still being able to read the number of digits involved. If not, if I get 0, then my machine cannot read any number below this point. Okay, so for example here, you can say that after 52 digits, okay, my computer is not able to read more than 52 digits. Because after 52 digits, I am getting y minus 1 equals to 0 instead of getting y minus 1 equal to x. So I will stop here. Okay. So for example here, I can read 52 digits, but remember, okay, in which base, in base 2. If you convert the equivalent number, okay, if I read the 52 digits after the decimal in binary number, it's equivalent in decimal system to 2.220446 times 10 to the power minus 16. So this is the order of accuracy I can have in case my computer is able to read 52 digits in binary base. Okay. Now, any other, if I increase number of digits after this, I cannot read anymore. Just pay attention that what is important for me, okay, is the, if you want, is the order of magnitude, the difference in order of magnitude. So I can tell you when I just say 52 digits, this doesn't mean I can just have 0 point, 52 digits after the point. But I can, because my computer can just put times 10 to the power any number. So if you have a number larger than 1, if you have 5.1, let's say, your computer can write it as 0.51 times 10 to the power 1. Okay? So when I say the number of digits it can read, I can have any combination of numbers by just multiplying by 10 to the power. Okay? Now what will be the issue is when I add numbers of different order. And we will see what will happen together now in examples.
Doctor, what is 0.5? You said it.
0.5 here, just you are applying this formula. هي 1 over 2 to the power 1. Okay? يعني أنا وقت أقول لك your computer can store 54 digits, you can write any number in this way. 0. Let's say 52, if you can read 52 digits, times 10 to the power 10 any power. يعني, the idea is the accuracy is to about 52 digits. Okay? Now, because you are putting your number in the form 0 point something times 10 to the power of a certain 10 to the power m, so this number, if you can read 52 digits up to 52, then your x will be 1 over the smallest number that you can read here as 0 point is 1 over 2 to the power 52. Okay? If you can just read 4 digits, let's say, if you can just read 4 digits, then you can just have after 0 point, the smallest number will be 1 over 2 to the power 4. Okay, now in the example, maybe you can understand it better.
Okay, so x is the smallest number that these number of digits can have.
Yes, exactly. Okay. What I want to emphasize also is, you can read a smaller number, but in a way, if you are not adding it to another number, what I mean by this, you can say that my computer can read 0.220446 times 10 minus 32. It can read it, okay? But if you add it to a 1, it will not read more than 2.22 times 10 to the power minus 16. You should look at the difference of order of magnitude, okay? For example, if I say I want to add 2.220460 times 10 power minus 32 to this number times 10, the same number, let's say, times 10 to the power minus 33, okay? Or let's say 30, okay? You can do it. Why? Because here you can transform this notation, okay? You can transform it in a way. So if you just put, for example, this number can be written as 2.220446, okay? You can, instead of 10 minus 32, divide it into 10 minus 16 times 10 minus 16, okay? So as I told you, the condition that when you add this number to another one, you should have a common coefficient here. Then you can, if you just add for it 0, your computer can read it because 0 is smaller than this number. So it can read this number and it will just put it as 2.22, okay, times 10 minus 16 times 10 minus 16. So your computer can read it because it can read a certain number after the decimal point. But if you add this number, which is 10 minus 32 to 1, then you are comparing two numbers, one of order minus 32, one of order 10 to the power 0. So the difference in magnitude is larger than 10 minus 16. Then it cannot read it. But if the difference in magnitude of the numbers you are just adding is not exceeding this number, it's fine. Okay, so we will see together in examples. You will understand it much better. We will give examples on this.
Doctor?
Yes?
You mentioned something about the binary, if they were the number of terms after the digits in binary. Could you, I didn't get it.
Where? Here? Yes. Oh, okay. Okay. Yes. Look. in general, how computer works. So a computer, when you give it numbers, okay, you give a certain number. Look, you will and I will give examples. If you still don't understand it in the example, I will go back to the slide, okay? Let us do the examples, and if anything is not clear yet, I will go back to it, okay? So let us consider just what is the way to define the machine precision. The machine precision is called machine epsilon also, and it's the smallest number for which if I do 1 plus epsilon, I get a number higher than 1. Okay, this is the definition of the machine precision. Now, how can what I can understand from the machine precision? So for example, for MATLAB, it's of the order of 2.22 to 10 minus 16. For Excel, it's of the order of 1.78 times 10 minus 50. To understand better what is the meaning of machine precisions, we will do some examples. And I will give you a smaller number so you can understand better. Let's say we are taking a computer that can only store 4 digits, okay? And I will consider that this computer is not working in binary base, it's working in decimal base. Because you can, it's, at the end, it's programmation. You can program a computer to work in base 2, you can program it to work in base 10. Actual computers and calculators work in base 2 in general, but you can do what you want. I can tell you in the exam, my computer can only store 4 digits and it's working in decimal base. And I want to add these two numbers. I want to add 1.557 and 0.041. Now, what is the conventional way to write a number? The conventional way to write it is to put it as 0. So here, between these two, the largest number is 1.557. So I can represent it on my computer. It can read it as 0.1557, okay, times 10 to the power 1. This is how my computer will read it, okay? Now, if I want to add any other number to it, I should make sure to write it in the same form. So I should multiply by 10, 1, both sides, to take 10, 1 into factor. Okay, so I will get then the numbers that I am adding to 0.1557 will be 0.0043. So if I want to write it in the same way of, so times 10, 1, I should add a 0 here. Okay, so it will be equal to 0.004341. So, and since my computer can just read 4 digits, okay, it will just read these 4, and it will disregard 41, okay? So now when I perform the addition, it's like this is my error, this is my round of error. For the first number, I don't have an error because already my number consists of 4 significant digits, okay? It's not affected by that my computer can only store 4 digits. But for the second number, when I add it to 1557, it cannot read 4 and 1. So it will just read 0043. When I do the addition, I will just get, my computer will just give me 0.16, while the exact value is 0.160041. So this is due to round of error, okay? Now what I want to tell you is that if you were adding this number to, for example, 0.01557, then the two numbers will be of same order, okay? And in this way, your computer can read 4 digits here and 4 digits here. Why? Because this number, you can write it then as 0.4341 times 10 minus 1. So just the condition is to have the same exponent here, same value here. That's it. If I have the same 10 to the power, same exponent, this is the condition to add. So here my computer can read this number if it's added to 0.01557 because they are of same order. So I can also write this number as 0.1557 times 10 minus 1. Okay, so I don't care for here. Here I can have whatever. I can have 10 minus 1, 10 to the power 2, 3, 4. I don't care. This can be easily identified by the computer. But now the two numbers I'm adding, I can just take 4 significant digits. So after the decimal point, I can just read these 4. And here I can also read these 4. So here, in this case, I will not, my round of error will be 0. Okay, because I was not, in this case, I didn't remove anything of my numbers. So I will obtain an exact value and the round of error will be 0. Now, if I add a digit here, if I want to now add 0.043411 with 0.15572, then in this case, my computer will not see 1 here and will not see 2. So I will have a round of error. Okay, so this is why I was telling you that in order to compute, if you want, the error I can have, it's this error is relative. So I can just multiply. If I have, let's say, if I am adding, for example, in the previous example, we were defining just with respect to 1 plus epsilon. Okay, so now if you want to add 1 million, let's say, okay, then the smallest number, okay, that you can add will be million times epsilon. So just if you multiplied 1 by 10 to the power 6, then the minimum number you can read compared to 1, okay, compared to 1 million will be just 10 to the power 6 times epsilon. So this is why I am telling you what you care for when you add two numbers is the difference in magnitude should not exceed a certain value. So you can always refer, so if you know what is the minimum number you can read when you add to 1, you can deduce the minimum number you can read when you add to 1 million, when you add to any, if you want, any multiple of 1. This is the idea. So once we get the precision error for 1, because you can always transform. So this number, you can transform it to 0.1 times 10 to the power 7. Okay, so this is why we define always with respect, we can define the minimum number we can read compared to 1 by just looking at how many digits we can read after the decimal point. Once this is achieved, we can deduce the error for any number. We can tell what is the minimum number we can add to it using this concept. Okay, is it clear now what we were doing before? Okay, so
Doctor,
yes,
we remove we remove what we don't need on the right before
yeah,
we add. What if we we have to do +1?
I didn't understand, Karen. Can you repeat the
Okay,
question?
can you go back one slide, please?
Yeah.
Okay. In the middle,
Yeah. Here?
you have instead of 0 0, for example, you have 7 1.
Okay.
We don't do 7 plus. لا محل الراد.
هون 7 1. The computer will not read them. It will
not read them. Okay.
No.
Okay.
It can only read 4 digits. Okay.
Yes, I thought. Okay.
No, he will not read them. Okay. Yes, we always write the number. Yeah, in general, the method is to put the number as 0 point something times 10 to the power. Okay, and you know from your computer how many digits he can read. So based on this, you can continue your calculation. Okay. Okay. So now these round of errors can become catastrophic in some cases. So for example here, if when you add, especially in the case you add a very high number to a very small number. So as I told you, what is important is the difference in magnitude. So higher the difference in magnitude, in order of magnitudes between the numbers, higher will be the round of error. So here, for example, if I'm taking the same computer that can only store 4 digits, 5,600, I can write it as 0.5600 times 10 to the power 4. And B, I can write it as because I am forced to have the same exponent, then I should add 4 zeros here to be able to write it as 0.00001 times 10 to the power 4. So this is very bad for me because now I can just read zeros, so I cannot read this number. I cannot read it. So it's true that if I just perform this addition and I calculate the relative error, I will find that my relative error is not very high because look, it's of the order of 10 minus 4 because I am just neglecting these two. So if I do the difference and I find the percent error, the percent error is not large, okay? But if I keep adding b infinite of times, my round of error will accumulate and it can reach bad stage. And if I add infinity of times b to a, my computer will read 0, 0, 0, 0. It will continue to read 0. So my error can accumulate if I have a lot of operation to perform. This is why we can solve this by having a highly precision machine. Okay, so if I increase the precision of my machine, it would be better. And plus that if I don't add, if I try to avoid adding very large to very small numbers, if it's possible. If not, I should increase as much as possible the precision of my machine to be able to add very large to very small numbers without losing accuracy. Okay. Now, to finish with this chapter, I will just give you a case where we can have combination of truncation errors and round off errors. Okay. So for example, if I tell you I want to compute f prime of epsilon x at 0. Okay, I want to use the forward technique and I want to use the central difference technique. So first, if I want to compute f prime 0, all I have to do for the exact value, I can get it easily. I derive fx, I get epsilon exponential of x. Once I derive it, okay, I can say that the derivative as 0 is exponential of 0, it's 1. Now I want to compare 1 with the value of the derivative obtained from forward difference method and from central difference method. Can I just take 5 minutes of your time? Already I explained this in the previous section. It's fine.
Sure, doctor. Yes.
Okay. So here you have, if you want to use the forward method, the forward method is f at xi plus 1 minus f at xi over delta x. Okay. So if I'm considering that xi is 0 here, okay. So simply xi plus 1 will be xi plus delta x. Okay, so if I replace xi by 0, I get, here they present delta x by dx. It's fine, but it is delta x. And when we put dx in, it's tending to 0. Okay, so it's 0 plus delta x minus f of x, which is 0 over delta x. So if I replace f of dx is exponential of dx. So this is the computation of f prime using the forward scheme is epsilon of dx minus 1 over dx. Now, if I want to calculate the true error involved, I take just, since I don't care for the sign, I take the absolute value of 1 minus the derivative obtained using the forward scheme. And I will repeat the same procedure for the central difference scheme. Now I will just take fxi plus 1 minus fxi minus 1. And you know that xi plus 1 is already calculated, it's 0 plus dx, while xi minus 1 is 0 minus dx over 2 times delta x. So now all I have to do is to replace f of dx by exponential of dx and f of minus dx by exponential of minus dx. And then I can find the function, and I can find the derivative expression function of delta x. I can vary delta x as I want, and I can find what will be the